We start into the day with Timo Derstappen talking about automating Kubernetes. Thanks for coming over, and yeah, it's your stage.
Hi everybody. Yeah, that's a very long title, and so in fact I'm talking about this running Kubernetes in Kubernetes. And who of you is using Kubernetes? Okay. Who have like played with Kubernetes or at least knows a little bit about it? Okay, good. So yeah, what is this talk about? I want to tell you a little bit about how we provision Kubernetes and what we learned in the last 1.5 years doing this. And since we're using Kubernetes to provision Kubernetes, there's also some advanced usage of Kubernetes itself, but it's not about giving an introduction into Kubernetes concepts, and yeah, obviously it's not using Kubernetes or deploying your own applications on Kubernetes. But since some of the things are quite advanced, please raise your hand, ask in the middle of the talk. Sometimes it's a little bit complicated to explain, so just raise your voice and ask. So I give you a little bit background what we're doing at GiantSwarm. So we manage Kubernetes clusters 24/7 for our customers. So we're not only just provisioning them and then hand it over to the customers, we are also on call for those environments. And we do this in data centers on bare metal, but also in the cloud, mainly on AWS at the moment. And yeah, we have this, we have our own data center in Frankfurt where we actually hand out Kubernetes clusters to customers as a service. So it's our machines and everything. We are just responsible for the whole infrastructure. And important thing about this is that we hand out like vanilla Kubernetes clusters that are, you have full root access to the clusters. It's not that it's like some like platform as a service where we cripple down the API and you're not allowed to start privileged containers, things like that. So you get a full Kubernetes and you can use the full Kubernetes as you can, like with your own Kubernetes. So the reference for us is always, if it runs on Minikube on your laptop, it should run in our Kubernetes as well, and it shouldn't be like the GiantSwarm version of Kubernetes. So I don't really like to say that this is the GiantSwarm distribution of Kubernetes, because we're just using the standard things that are coming from the community, that have been accepted by the community, and that are in most of the Kubernetes clusters, and we support them. And it's not that we have like our own layer on top of Kubernetes. And we also do this on premises in the data centers of our customers. So we install our stack in a data center of a company, and then we maintain this stack, we update it, and we are on call for it. So if an enterprise wants to have a Kubernetes environment, we also do this inside their data centers. And all the tooling, everything I'm talking about is open source. So the things we do to provision Kubernetes clusters, it's all on GitHub. It's not downloadable as a package and then you just run it at the moment. But still all those bits and pieces are out there, and yeah, we're giving this kind of talks to encourage people also to look into it. There are also a bunch of other companies working with us on those components, and we're close to the community to actually see how we can improve the lifecycle management of Kubernetes clusters. So that it's actually something that goes upstream, that every Kubernetes installation would benefit from, that it can manage itself and stuff like that. So a little bit about the motivation why we're provisioning multiple Kubernetes clusters. So in a dream scenario, you would have just one Kubernetes cluster in your data center, and you can schedule all your workloads on this cluster. That would be ideal, but we figured out that lots of companies are not there yet. So most of the companies wants to run multiple Kubernetes clusters. They have teams that work with, I don't know, financial data, privacy stuff, and they want to have them separated from other teams that are doing some web applications, and also they're used to having environments for pre-prod, prod, and then separate them from dev and test, and they don't want to have these workloads mixed in a cluster yet. And also there's always the need, if you have a build pipeline that integrates with the Kubernetes API, that you have like a test bed where you can spin up a cluster with a new version and test out your build pipeline. Does it still work with the new Kubernetes version and stuff like that? So we also make this easy to spin up a new cluster with a different version and test everything. And yeah, so we figured out that people must come to things in their own time, in their own way, for their own reason, or they never truly come at all. Because Kubernetes has role-based access to narrow down the machine-to-machine and the user-to-machine communication within a cluster, and this is fairly new, but still the direction is clear that that there's a lot of security features and a lot of new concepts in Kubernetes as a container platform that maybe at some point will also be accepted by security in those companies, but they need to gain trust that, for instance, something like Calico and the network policies as a dynamic firewall are doing the same thing as your old appliances that are manually configured, where you have your zones and you separate your application and your presentation and your data. So that's where where those people in the data centers are coming from. That's what they're used to, and obviously the technology is quite young. So it just needs some time to gain trust, to understand how it works, to see how the concepts make sense. And so we encourage people to use all this in their clusters. And we're helping them to, we even had role-based access in 1.5 clusters running, and it was just a little bit more work to do. And those people using the clusters learn about those features and gain more trust. So what I'm talking about now is internally called Giant Neatest, because it's the Kubernetes that spawns Kubernetes for our customers and for our clients. And the motivation is quite obvious. We are providing Kubernetes because we think it makes sense to deploy application that way, and that Kubernetes has the right building blocks to do so. And why should we then use Ansible to provision Kubernetes again? Because we don't want to do that anymore. And so we came up with the idea to use actually Kubernetes to provision Kubernetes. We still have this chicken egg problem that we need to provision the first cluster, and we have some Ansible scripts for spinning up the first node in an environment at the moment. And also in AWS, we're using some Terraform. So there's still some of the configuration management tools that you probably know. But once this is up, everything is automated inside Kubernetes itself, and there's no Ansible anymore. And so a short definition, because it's confusing. This is a shortcut for Neatest, and that always means the host Kubernetes cluster, the underlying, the mother of the Kubernetes is, this is the Kubernetes. If I'm talking about Kubernetes, it's always the tenant cluster, the guest cluster that we're providing for our customers. And don't confuse it with Kubernetes. That's what the people from the US call it. And it's a nice restaurant you can go to, or you can take out some food. So, architecture. Yeah, as I said, a little bit confusing sometimes. So there are just 3 roles in speaking to our control plane, which is we, who provide the host cluster and the tooling. So we're the Neatest admins. Then somebody is the cluster admin. So somebody creates a cluster on our system. And for instance, he can like create key pairs and then hand them out to developers who wants to use the cluster. And then, yeah, the developer is the cluster user that actually puts stuff on the cluster, or maybe that's the build pipeline. And then next to it, you have the actual nodes running as an application zone. So you have a separation of, this is controlling the infrastructure, some monitoring is in here as well. We have some services that are, we're using Vault, we're using a distributed file system called Quobyte, and we're using some other like networking and those kind of services that we're running here. We have our own API and our own services that allow the cluster admin to actually create the cluster, and here we have the like dump nodes running where people can schedule their workloads on. And so if you blow this up, this looks a little bit more like this. So here are the clusters, the different ones, and traffic comes from here. From the outside, and you can separate this from like traffic who has access to the control plane and stuff, and you have some dashboards here and some other tools, and yeah, but it doesn't really matter. And then if you blow this up here as well, it looks like this. So that's a tenant cluster, a Kubernetes cluster, and like a typical architecture of a Kubernetes cluster. Where you have like a controller, a scheduler, and you can run some dashboards on it. You have the API server, and these are the workers, the worker nodes, where you schedule your workload on, and then you can use, kubectl. You need a registry, those kind of things, and then inside the workers usually also have like an Nginx controller, and you have an Ingress controller. We're using the Nginx controller. You would have kubedns and a couple of other things running in there, like the network policy controller and so on. So within our setup, the master is completely managed, and nobody has access to the master itself. But on the workers, as I said, you can start privileged containers, and you have like full access to it. And why are we doing this again? We just want to fully automate the complexity I've just shown. So there are lots of bits and pieces in the infrastructure, lots of tools that also have independent an independent lifecycle. So there's like a new release of Calico and a new release of Flannel, and Vault changes and Cobite and whatnot, and Kubernetes, and so there are lots of bits and pieces in there. And we just want to have this fully automated, and also have something that takes care of the life cycle of those components while they are running. So not only just provision them and then hand it over, but also manage the life cycle. So having frequent updates in your cluster, and not like every 6 months. Oh, we do this like huge upgrade of Kubernetes now, and then everything fails. And yeah, we just doing all this complexity to take away complexity from the developers. Yeah, one thing that is really important to us there is that we have full immutability. So we're using CoreOS for the underlying host, but also for the tenant clusters we're creating. And yeah, we have like a continuous pipeline where we build our images and then push the images to a registry, and then also apply those changes to Kubernetes automatically. So that means for our services, that happens on the giant Neatest, on the underlying Kubernetes. So our services are running in there, and then if somebody upgrades a component, it's automatically deployed. And but we also do this for the tenant clusters. And yeah, that gives us reproducible builds. We can create the same build forever. We can create the same deployment at any point in time. And it's not something that just lives and is like idempotently patched all the time, and then you didn't pin this library or that library, and slowly everything diverges from what you would create if you created now from scratch. So you can also like easily automate, like spin up a cluster, do some testing, tear it down, and do it again. Yeah, and every manual change on the systems is ephemeral, because we're also kind of managing what should not be on the machines. Because if you have like some scripts that go to your machines and install something, you probably don't remove things that shouldn't be installed. I mean, who's doing that with Ansible? Removing every package that shouldn't be on your machines. Yeah, I didn't do that as well with Ansible. But if you have everything immutable and you frequently change your images, you frequently change the machines, the containers, at some point manual changes will just be gone. So everybody who does something needs to persist it somewhere within the stack. Yeah, and meantime to recovery, those clusters are pretty fast. So if you create this cluster in under a minute, you have a fully working Kubernetes cluster. And yeah, that's also important. So if shit hits the fan, you are still able to recover quite fast. And yeah, some detail about the networking. So, I mean, how are we doing this with creating Kubernetes clusters with Kubernetes on bare metal? So we actually start KVMs in pods. So just imagine creating a deployment in Kubernetes that has a replica set that says, okay, I want to have 3 workers, and then Kubernetes takes care of creating these creating 3 containers with Chemo tooling in that start VMs. And then inside the VM we have again CoreOS and form the cluster across those nodes. And this sounds a little bit weird, but the container is just a package that we use to have the Chemo tooling, because CoreOS doesn't have that. And then it's just spinning up a KVM process inside the container namespace So there's like not really overhead involved there, and I mean the KVM overhead obviously, and it's quite handy for us to do so, and so we're using Flannel to connect, and actually this is old, we're not using the Flannel server anymore. That was a experimental feature. We're just using the Flannel here only. So we're connecting the VMs outside of the VM through Flannel. So usually if you have a Kubernetes setup, you would use Flannel in a different way, but we're using it to actually connect the VMs across the hosts. We're using a VXLAN backend in Flannel, and so they will be in the same VNI and can talk to each other. And then inside we're using Calico to connect all the containers between each other. And then you can have like a different tenant on the same physical machines that are also connected through a different Flannel bridge and have Calico inside. So Flannel does the tunnel for the VMs. Since it's outside, nobody inside the VM can change that, and Calico is there to connect a container from one host to the other. We also do, so every component in Kubernetes has TLS obviously, and so we create a root CA per cluster automatically in Vault. Vault has a PKI backend that you mount, then you can create your root CA, and then you can create a role and tokens for those roles that are allowed to issue certificates of certain domains and TTLs and stuff like that. And since we're able to do this, we're in an automated way, we're rotating them every day. We did this for a while with like a couple of minutes, and we found a lot of bugs. So it was a nice resilience test doing so, but one day works very well. And actually, Kubernetes doesn't check revocation lists, so rotating shortly makes sense, because you cannot revoke a certificate, and because the Kubernetes components wouldn't check the revocation list for performance reasons. And to avoid that it fails, and then after one day you're screwed. Actually, we're currently using a TTL of 3 days, so it's a little bit of time to get the certificates set up. If I don't know, Vault fails on a day, we're not screwed. And most of the Kubernetes components have mutual TLS even, so you have client and server certificates, and this is also that can be used in authentication as a basis for RBAC. So the role-based access depends on the common name or the organization in the certificate. So the common name is your user, and the organization is your group that you belong to in the role model of Kubernetes, and so it's also used for RBAC there. So yeah, operators. So we went through some iterations with that platform. So in the beginning, we have been using CoreOS for quite some time, and we have been using Fleet very heavily. And so in the beginning, it was the easiest thing for us to put systemd units with the Kubernetes components, or with this Docker containers that spin up VMs on Fleet. And we created the clusters like that. Then we thought, okay, it would be better to ditch Fleet completely. We're the only users of Fleet, and nobody else is using that anymore. So let's move on. So why not using Kubernetes for it? So we started out just writing our YAML files for a cluster, and then doing like kubectl create, and then all the bits and pieces of a cluster were created. And at some point we started automating this because we didn't want to have like templating config management anymore. So we started writing operators. And operators, so operators is a term that actually Core has coined. The alternative name would be custom controller. So it's basically about writing your own Kubernetes controller. And we're doing this to do all the things automatically that we have been doing manually as operators. The goal is managing desire state. You say, I want to have a cluster with these and these nodes, and then the operator takes care to transform that to the actual state. So that's how Kubernetes works in general. So you say, I want to have 3 pods, and then Kubernetes, the internal controller, takes care that actually there are 3 pods, and if you kill one, Kubernetes will take care to just spin up a new one. And so for doing this, the API server is quite dumb. It's just CRUD operations. So you have like a key value store. So you create a resource in the API server, and then there's something else that watches the API and sees like, okay, I have like 5 pods. Okay, now I have 6 pods. And then it does a reconciliation loop with the existing things and sees, okay, I see 5 pods, so I need to spin up 1 more. So that's the loop a controller is always in, watching the API, seeing what's defined, the desired state, and then listing what's actually there, and then trying to apply the difference. That also means removing one if you define it should be 1 less. And to do your own extension of the Kubernetes API, it's quite simple to create a third-party resource. So Kubernetes comes with a bunch of resources predefined. That's pods, services, jobs, daemon sets, replica sets, deployments, ingress, lots of concepts that are in Kubernetes where Kubernetes has a controller for, or ingress is a little bit different where there are external controllers for it. But you can also create your own resource. So for instance, I don't know, if you want to write a shop system on Kubernetes, you could create a third-party resource called shop, and you put some attributes in this third-party resource. Just think of it as like a database schema that you create. So it would be like what kind of theme, what kind of URL, what's the title of the shop, things like that. Put them in the third-party resource, and then write your own controller that sees, okay, somebody created a new shop, so I need to do like create this pod, and this pod, and so my shop instance is created. That's what you can do with. Oh, I jumped 1 slide. That's what you can do with third-party resources. You can easily extend the Kubernetes API, but you also have to write your own controller for it. And so what we did is we created a KVM operator that defines a cluster third-party resource in Kubernetes. And so it has some attributes, how a cluster looks like, and then the KVM operator actually translates the cluster definition into the actual pods that need to be running. I mean, there's more to it than pods. There's ingress, and there are some jobs, and there are services, and stuff like that. So it would just create all the necessary Kubernetes native resources. So translating our abstract model of a cluster into the real Kubernetes concepts. And we did the same thing for AWS with the AWS operator. So you can still do like kubectl create cluster. So you have a cluster YAML where you define your cluster, and and the AWS operator would actually do the reconciliation loop with the AWS API. So it checks with the Kubernetes API, hey, how many clusters should be there? And then checks with the AWS API, are the clusters really there and created, and are all the components there? And so the workflow looks like this. So the cluster admin creates, and ignore our services here, because in the end we're writing the TPO, which is the third-party object. The resource is the schema you define, and then the object is the instance, like the row you insert into your database. And so so here you see everything is empty. This is the host cluster Kubernetes state, and then our services write a TPO to the Kubernetes API. So we create a cluster object, a CA object, and multiple objects for certificates. And then our operators, so you can see the CA operator will pick up the CA TPO and talk to Vault and create the backend in Vault, and creates the root CA, creates the necessary roles, and then the third operator is able to issue the certificates based on the list that was given in the third TPOs. And then the KVM operator is able to actually create the cluster itself. And then you see, like from here to here you see you have no pods, and suddenly you have Flannel running, a master running, workers running inside the host Kubernetes. And yeah, similar on AWS, but then you don't get pods in here, but actually the AWS operator talks to the AWS API. And typical things that are in those cluster definitions are, configuration and versions, and so yeah, it's a huge list of YAML attributes that didn't fit on my screen. So sorry for not giving you some examples. But yeah, it's basically what you would do in a templating configuration management as well. Most of this stuff is just hold in config maps in Kubernetes. So if this is in the TPR, but then it's translated into config maps and secrets and all these native components in Kubernetes. And yeah, similar for the certificate TPR. So you have a TTL, you have a common name, you have some alternative names, and yeah. Questions? Because we're nearly end to my talk. Yeah.
So on AWS, you basically skip the KVM stuff and you just use the API to.
Yeah, it didn't make sense to have like nested virtualization in the EC2 instance. Yeah.
So QEMU and KVM are only needed on bare metal.
Mm-hmm. Yes. Yeah. Other questions? Yeah, so one learning for us was, yeah, we should use very small operators and not build too big operators that do a lot of things. I mean, the CA, the cert operator, and the KVM operator is already a nice separation. For instance, we're currently doing some DNS stuff inside the operator, and we would like to separate that out into DNS operator that is then, like, if you create a DNS TPO, then you have an interface, and then you have like the DNS operator talking to Cloudflare, talking to Route 53, to whatever you want to talk to, actually create the DNS entry. That would help, and not having this inside of the KVM operator and then again inside the AWS operator, but slightly different, those kind of things. One colleague wrote a pingdom operator. So for every ingress in a cluster, the pingdom operator creates a check on pingdom, which is quite nice. And it's like nearly instant. And you remove the ingress, like you remove your service from the cluster, and it's instantly removed from pingdom. And that's quite nice. And you have this nice decoupling of things, where you have something that takes care of translating this. I mean, it doesn't need to be a pingdom specific definition. It's just based on the ingress resource that is anyway in your cluster. So the pingdom operator just watches the ingresses that are anyway there, and then talks to pingdom and creates this. But you could do that with any other monitoring system as well. And yeah, so keep them small. Have like a focus of that operator makes sense. We also finding more and more that we have some boilerplate code in the operators, so you're always doing the same thing in the operators, and so we are putting some of our code into a library at the moment. We have a library based on GoKit for our microservices called MicroKit, and we want to do the same thing for operators. So we're having operator kit. And one important thing, I think that's the most important thing with upstream Kubernetes is the whole community is heading into having self-hosted Kubernetes clusters, and that's also very important for us. So self-hosted Kubernetes means another type of inception. That would mean the components that form Kubernetes would run inside of Kubernetes as well. So inside the same Kubernetes. So you spin up a Kubernetes cluster, and then the bits and pieces that form the cluster are actually parts inside of the cluster. So you could do a rolling update of a kubelet, and every Kubernetes cluster is able to do that with itself. So that would be easy for us to just delegate that to the clusters. So if the outer cluster says, our cluster spec says, okay, we want to now have like 1.6.3, then you change this in the cluster TPR, and our cluster operator, the KVM operator, would just delegate this to the inner cluster and say like, hey, you should upgrade your pod, and please do a rolling update of your kubelets. And that's much easier, and that's something that every Kubernetes installation would benefit from. So currently the SIG lifecycle is working on making this a default in kubeadmin, having self-hosted clusters. And yeah, we're also working on this. So that's kind of important to achieve to make the lifecycle of Kubernetes clusters easier in general. Yeah. Thank you.
Are there any questions?
So what does the current workflow look like when you upgrade Kubernetes?
Currently we're not upgrading in place. That's something we're working on, especially also because we don't want to invent something separate from the community. That doesn't make sense for us. So we want to do that with the community to have a nice way to upgrade clusters. So at the moment is you create a new cluster with a new version. That's the current state.
And then it moves your apps automatically.
Yes, yeah, yeah. I mean, we did quite a lot of rolling updates of clusters as well, but the operator version of our system doesn't yet support it. So in the older versions of the platform, we're just rolling nodes. So we're creating a new image like a new container image with a Chemo tooling that has templating for the cloud configs. So we're starting the KVM with CoreOS, and then we're changing out the cloud config, and then it starts up a new node with a new version. And we could do the same thing with operators, and we're probably doing something like that. But we also want to see what's going on upstream to have. The goal is definitely to have self-hosted clusters and not to invest too much time into tooling around that will be obsolete in a couple of months. Hopefully it's a couple of months. It could also take more than a year. You don't know. So yeah, our customers definitely have the need to upgrade, and that sometimes depends also on what are they running. Not very many are running a lot of state in containers at the moment.
Okay, thank you. More questions? Come on. I know it's early, but anyway, also for him. We have plenty of time.
I have some coffee, yeah.
Yeah. Any questions? Somebody needs a wake-up call? I don't think that I can force somebody into, because I would like to.
How are you running Kubernetes? I mean, there are 3 people running Kubernetes. What are you using to provision? I can ask questions.
Yeah, at Booking we're running Kubernetes on bare metal, and we have our own bare metal provisioning system, a thing that we wrote ourselves and that we are currently running to basically control all of operations.
So it's your own Pixie boot system, or?
It's a bit more than that. It's actually too much on a single thing. There is a system called ServerDB, and there's a thing called NEMU. ServerDB does all of data center operations, inclusive asset management and stuff. It's not just Pixie boot. Mm-hmm. And NEMU does all network operations, and that is everything from router and switch configuration to, again, line management and stuff like that. It's 2 very huge, awfully written, giant Python Django applications that basically control the entire data center. But nobody does anything manually. We are just clicking the web interface or talking to the Django REST API to do stuff, which is pretty convenient. And inside that, we then run also our various Kubernetes clusters. There's more about that later today in my talk then.
Cool.
Okay, we already hit the marketing part. Well done.
Who else is running Kubernetes?
There was one over there, right, with experience? I don't know.
I mean, you can also say what's a pain in your setup. Yeah, we also have our own Pixie boot system that we're using to spin up CoreOS. We also open source that. There's also Matchbox from CoreOS that does something like that, where you can provision your machines with CoreOS images and have some templating around cloud configs, because you need to have services configured that spin up the cluster. What we're trying to do at the moment is to reduce that to a minimum. So we have been using systemd with Fleet heavily, and we did all this, but at the moment we're trying to reduce the footprint in the cloud config or in Ignition to have like as low as possible in there, and to have something like kubeadmin actually taking care of creating the cluster, because that's what's in the upstream, that's used in the upstream community. So if we create a cluster with kubeadmin, it's more likely to be a cluster that is common to the community, and that's our goal, to have a vanilla Kubernetes cluster that is not different from lots of other installations, and that would also reduce some of the JSON and or YAML definition we have in our cloud configs. That sometimes makes it a little bit complicated.
You mentioned a pingdom monitoring before for ingresses that are automatically added to pingdom. And what I'm wondering is, if is something that monitors your deployments and services and maybe pods or even containers for their availability state. So I know there's lots of people using Prometheus for Kubernetes monitoring, and I think it's already somehow included. But is there anything, or is there even the need to monitor the availability of all these components that are building the cluster and building the application?
Yeah, it's like doing unit tests and integration tests. So you need to have an end-to-end test through your stack from the outside, in my opinion. And you also need to monitor inside to actually see what smaller things are breaking. That gives you more insight. So we are usually doing both, and we also have like a test bot in running inside the clusters and also in the host cluster that is able to continuously create a cluster and check a few things, and does it still work, that you can create a cluster, those kind of things. So having end-to-end tests, integration tests, that makes sense next to having monitoring on internally inside. I mean, you could also do just monitor your inside monitoring system from the outside and check that it's available, and then test internally. Yeah, we also doing this for endpoints that should be available to the outside, that we are monitoring them from the outside.
Okay.
Yeah, Prometheus is not included in Kubernetes, but Prometheus is part of the Cloud Native Foundation. As also, so there's Fluentd for shipping logs. There's Open Tracing, Prometheus, and yeah, there have been some recent additions, Linkerd, and I don't know, but a couple of projects, and these together form the cloud native stack. So usually our expectation is that projects that are in the foundation also fit better with Kubernetes than other solutions. That's not always true, but at least they are like in a family somehow.
Okay, I think we are through it. So thank you, Timo. Warm applause for you.
Thank you.